Next objective, the student will be able to graph and identify properties of rational functions. Rational functions pretty much means fractional. There's a numerator and a denominator, a top and a bottom. A rational number is fractional in a way. You can write it as integer over integer. A rational function is fractional. You can write it as polynomial over polynomial. Okay? So polynomial over polynomial, and the top polynomial we could call n of x, and the polynomial in the denominator d of x. And so here's an example. Okay, x plus 5 over x minus 2, that's a rational function. Domain is the set of all real numbers of x with the exception of 2. Okay, so domain is a set of all real numbers x such that x is not equal to 2. Why is that? I'm sure you realize that a 2, the number 2 in here, zeroes out the denominator. You're not allowed to divide by 0. X is not allowed to be 2. 2 is not in the domain of f of x. Vertical asymptotes. What is an asymptote? An asymptote is a line that a curve approaches. A line that a curve approaches. So a vertical asymptote is a vertical line that a curve approaches. X values at which the function is undefined represent vertical asymptotes to the graph of the function. In most cases, a vertical asymptote is a line of the form x equals k, right? That's vertical, right? If it's x equals a number, then you've got a vertical line. And the graph of the function approaches it but does not cross it. In the figure below, which is the graph of our rational function x plus 5 over x minus 2, we've got that vertical asymptote, that vertical line that the curve approaches, the line x equals 2. And the curve, of course, is going to approach it. It's going to get closer and closer and closer and closer to that line. It will not touch it. A horizontal asymptote of a function is a line that has equation of the form y equals k. We recognize that as the form of an equation of a horizontal line. Y equals just a number, which the graph of the function approaches as x approaches plus or minus infinity. So as x goes infinitely to the right or infinitely to the left, the graph approaches that horizontal line, which in this case is the line y equals 1. Right? We've got a line here which is 1 unit above the x-axis That's the line y equals 1. The curve approaches it as x goes to infinity or as x goes to negative infinity, as we go very far to the right or very far to the left. Generalizations about asymptotes of rational functions. Vertical asymptotes. Suppose the numerator and denominator have no real zero in common. In other words, your rational function is in lowest terms. Okay, you can't cancel anything. It's in reduced form. Then the line x equals c is a vertical asymptote if d of c equals 0. So in other words, the line x equals a 0 of the denominator. 0 of the denominator. That number, whatever it is, like 2. A 0, of course, is just a number that makes your expression 0. And 2 does that in the denominator. If you have x plus 5, I believe it was, over x minus 2, then 2, that same number that we had to exclude from the domain, as it turns out, that was where the vertical asymptote is. Now, case 2, if they have one or more real zeros in common, then you cancel the linear factor and apply case 1, which just means that if you can cancel something, cancel. Okay, simplify, reduce your rational function to lowest terms if you're interested in finding the equation of the vertical asymptotes. Horizontal asymptotes. Case 1, okay, there are 3 easy cases. Okay, so you have you've done the vertical asymptote problem. Okay, so if you're asked to find all asymptotes, you first find your vertical asymptote, then you find your horizontal asymptote, and then, if necessary, if there is no horizontal asymptote, you will go ahead and find an oblique asymptote, also known as a slant asymptote. But we're just interested in horizontal asymptotes right now. So horizontal asymptotes, that's an easy problem. Of course, vertical asymptote, that was an easy problem. You just cancel whatever you can, and whatever your zeros of the denominator are, that is where you're going to have your vertical asymptote or asymptotes. Horizontal asymptote, this is an easy case because you've got 3 possibilities, but the results are just pretty much automatic. Now, if you have 2 things, 2 numbers, one is either less than the other, the first one is equal to the other, or the first one is greater than the other. And here, the 2 numbers are the degrees of the top and bottom. For f of x equal to x plus 5 over x minus 2, the degree of the polynomial in the top is 1, and the degree of the polynomial in the bottom is also 1. Now, if degree of the top is less than the degree of the bottom, okay, you know, maybe that x were not there. Maybe you have g of x equal to 5 over x minus 2. Then automatically we have the answer to the horizontal asymptote problem. It's the line y equals 0. That is a horizontal asymptote. The line y equals 0, also known as the x-axis. It's automatic, okay? We call such rational functions proper, just like a proper fraction. Okay. So that's easy. Degree of the top is less than the degree of the bottom. You know, in our example here, the degree of the top was degree of the top was 0, and the degree of the bottom was 1. But now let's let the degree of the top equal the degree of the bottom. Then the answer is pretty much automatic, okay? Y equals a over b, where a and b are the leading coefficients of the two terms. Now, this is case 2 is where f falls, right? F of x, the degree of the top is 1 because it's x to the first, right? The degree of a polynomial is the highest power of x. If we're talking about a polynomial in one variable x, which we are in this section and in this chapter, and degree of the bottom is also 1. Well, 1 equals 1. 1 equals 1. And so we're in case 2 here. Now, when that happens, the horizontal asymptote, of course it's a horizontal line, so its equation will have the form y equals a number. And in this case, y equals the ratio or fraction ratio of lead coefficients. Okay, so you learn to just look at the rational function and be able to tell immediately what the horizontal asymptote is. Of course, in this case, the lead coefficient of the top is 1 because that x there is a 1x, just like the x in the denominator. That's a 1x. And so 1 over 1 is the number that we have for the horizontal asymptote. So horizontal asymptote is y, the line y equals 1 over 1. That is the line y equals 1. That's the answer. And we, of course, we've seen that already. We've seen that horizontal line 1 unit above the x-axis. So that case is also easy. Third case is really easy. If the degree of the top is greater than the degree of the bottom, then there just is no horizontal asymptote. And so if you're asked to provide one, your answer is there isn't one. And so all three cases are easy. They're automatic. You look at your horizontal function and you know the answer without even calculating anything. Generalizations about asymptotes of rational functions in formalized. Okay? So, same thing as what we were just saying. degree of the top less than the degree of the bottom, it's y equals 0. That's the answer. Okay, so if you're asked, find the equation of the horizontal asymptote. Degree of the top less than the degree of the bottom. The answer is, whoops. The answer is the line y equals 0 is the equation of the horizontal asymptote. And you are required to write y equals 0. Don't just write 0, okay? That is not really a right answer, because if you're asked to find the equation of the horizontal asymptote and you put a number is not an equation, okay? And so the right answer is y equals 0. Case 2, if the degree of the top equals the degree of the bottom, y equals the ratio of the lead coefficients. That's the equation of the horizontal asymptote. And we close with the definition. If the degree of the top bounded function greater than the degree of the bottom, function is f is bounded if the entire graph of f lies between two horizontal lines.